Bismillah ar-Rahman ar-Rahim. Today we will talk about chapter 26, direct current circuits. In this lecture, lecture 1, we will discuss the resistors in series and parallel and Kirchhoff's rule. In the second lecture, we will talk about the RC circuits, concepts, and theory. Let's start by the first part of this lecture, resistors in series and resistance in parallel. The resistors can be connected in series and can be connected in parallel. When they are connected in series, for a series combination of resistors, the current in the two resistors is the same. This sentence is very important. So what do we have? In this circuit, the current I is the same for the resistors, for the resistance R1, and it's the same for the resistor R2. So why? Because they are connected in series. What about the potential difference? The potential difference is not the same. So let's say this is delta V1, the potential difference across the resistor I1, R1, and this is delta V2, the potential difference across R2. So what will be the total potential difference across the two resistors, delta V, which is equal to delta V1 plus delta V2. Okay. In another hand, these two resistors can be replaced by just one equivalent resistance, where the equivalent resistance in series, it will be R1 plus R2. Why? Because as you know, delta V equal delta V1 plus delta V2. So this is for the series, and we have the same current I. So if we want to apply Ohm's law, so what we're going to get, delta V1 equal R1I, and delta V2 equal R2I, because we have the same current. So at the end, we get delta V equal I factor of R1 plus R2. So what will be the total, the equivalent resistance? Delta V over I equal R equivalent. So R equivalent will be, in this case, R1 plus R2 in the series combination. It's okay. So let's make a short conclusion. So for the two resistors in series, connected in series, we have R equivalent is the sum of the individual resistance. The equivalent resistance of serial combination is always greater than any individual resistance. So imagine that we have, for example, this is 1 ohm, imagine, and this is 5 ohm, and this is 10 ohm, etc. What will be the equivalent resistance? The equivalent resistance must be greater than 10, because here we are adding some positive resistance. Okay, so it's always greater than any individual resistance, or we can say it's greater than the greatest resistance in the circuit. Okay, so in general we can say that the equivalent resistance in series combination, it's the sum of R1, R2, R3, and so on. If all the resistors are identical, if we have n identical resistors, in this case, R equivalent in the series combination will be n. That means the number of resistors multiplied by the resistance. This is when we talk about identical resistors. That's all for the series combination. Now let's move to the parallel combination. In the parallel combinations, the potential difference across two resistors are the same. Why? Because we are talking about a parallel combination. So here we have the same delta V for R1 across R2, and it's these two resistors are connected parallel to the power supply. That means all of them, they have the same potential difference. Now, what about the current? According to loop rule that we will talk about it in the second part of the lecture, the current I will be divided into two currents, I1 and I2. Okay, so we can say that delta V1 equal delta V2 equal delta V. This is the first relationship when we talk about parallel combination. Okay, and we have another equation, I equal the initial current equal I1 plus I2. Combining these two equations, we're gonna get the current I equal delta V multiplied by 1 over R1 plus 1 over R2. Okay, so what we're gonna get? So we will get delta V equal I R equivalent when we are replacing these two resistors by just one equivalent resistance. Ohm's law said that delta V equal R equivalent multiplied by the current I. So in this case, we can conclude that R equivalent is R equivalent. So we can say that R equivalent in this case is 1 over R1 plus 1 over R2 plus between bracket power -1. Okay, so this is R equivalent. Or we can say also that 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over Rn. So we have to continue here the calculation to get R equivalent, not 1 over R equivalent. So we are done with this part. In this parallel combination, the equivalent resistance is always less than the least resistance in the group. For example, let's take R1 equal 1 plus R2 equal 2. R equivalent in this case will be 1 over 1 plus 1 over 2 power -1. R equivalent must be lower than the lowest, which is 1. R1 equal 1. Okay, so it must be it must be lower than the lowest resistance in the circuit. For the n identical resistance in parallel, 1 over R equivalent, it will be n multiplied by R, or we can say R equivalent will be R over n, and n is the number of resistance in the resistor in the circuit. Okay, for a series combination of resistors, the current is the same. The current in the two resistors is the same. For the parallel combination, more current goes into smaller resistors. More current goes into smaller resistors. Because, as you know, for the parallel, we have the same potential difference delta V. So that means delta V equal R1 I1, which is equal, because they are parallel, R2 I2. So what we can conclude, we can say that I1 over I2 will be equal R2 divided by R1. So if we're the more current will be going through the lowest resistance. Okay, if this is greater than 1, that means I1 is higher than I2. In this case, R2 must be greater than R1. Okay, so when we talk about the higher current, that means we talk about the lowest resistance. When we talk about the lowest current, that means we talk about the highest resistance. Okay, let's move to some applications. 4 resistors are connected as shown. Find the equivalent resistance between the point A and C. So let's start by these 2 resistors. These 2 resistors are connected in series, so they can be replaced by just one equivalent resistance, where the resistance equal R equivalent for the series equal R1 plus R2. So in our case, it will be 8 plus 4. So let's write here 8 plus 4. 8 plus 4, it will be 12. Good. These 2 parallel resistors, they can be replaced by just one equivalent resistance, where R equivalent, in this case, R equivalent for the parallel will be 1 over 6 plus 1 over 3 power -1. So we're going to get 2. Okay, now we have 2 resistors are in series. So the equivalent resistance will be their sum. Okay, so R equivalent of the circuit will be 12 plus 2, which is 14. We are done. Let's move. Question B said, what's the current in each resistor? If the potential difference is 42 volt is maintained between the point A and C. Between the point A and C, we have 42 volt. So also here for the equivalent resistance, we have 42 volt. Okay, so here what will be the current? The current I in this case would be 42 divided by 14, because we have to apply Ohm's law. So we have I equal 42 divided by 14, which is equal 3 ampere. So the current between A and C, or the current going through the 14, the equivalent resistance is 3. Now, because these two resistors are connected in series, so they have the same current. So what's the current going through the 8 ohm resistor? It's I, and I how much? 3 ampere. The same thing for the 4 ohm resistor. They are connected in series, so they have the same current, so the current will be also 4 ampere. Okay. Now let's move. For that, we said the total current I passes through the 8 ohm and the 4 ohm resistor is the same and will be equal to 3 ampere. Okay, now what's happened to the current at this junction B? At this junction B, the current will be divided into two currents, I1 and I2. So we can write that the current I, the total current I, will be equal to I1 plus I2. Very good. However, I is equal to 3 ampere, as you know. And these two resistors are connected in parallel, so they have the same potential difference, delta. Delta V between B and C is equal to, delta V between B and C is equal to the current I1 multiplied by 6. And in the other hand is equal to the current I2 multiplied by 3. Okay, so what we can conclude, we can say that at first we can simplify by 2 by 3. So here we're going to get 2, and we can write like that. We can write that. So as you know, delta V between B and C is the same for the two resistors because they are connected in series. So it's gonna be I1 multiplied by 6. This is from one hand. From the other hand, it will be I2 multiplied by 3. Here we can simplify by 3, and we're gonna get the relationship to be 2I1 equal I2. However, don't forget that we have a loop junction, sorry, so we're going to get 3, the total current equal I1 plus I2. If we substitute here I2 by 2I1, so we're going to get 3 equal I1 plus 2I1. So it would be 3I1 equal 3. So in this case, we can conclude that I1 equal 1 ampere. Okay. So to calculate I2, we know that 3 equal I1 plus I2. So that means 3 equal 1 plus I2. So I2, as a result, will be 3 minus 1, which is 2 ampere. And like that, we already calculated the 3 currents going through each individual resistor in the circuit. We are done. Another example, 3 resistors are connected in parallel as shown. So these 3 resistors are parallel, and all of them, they are parallel with a power supply 18 volt. Okay, a potential difference of 18 volt is maintained between the point A and B. Find the current in each resistor. As I said, all of them are connected in parallel, so they have the same potential difference. So we can say that delta V, which is 18, equal I1 multiplied by the resistor. So we can write 3I1. 3I1. So we can conclude that I1 equal 18 over 3, which is 6 ampere. We are done for the first one. We do the same thing for the other resistor. So we're gonna get delta V over R2 equal I2, delta V over R3 equal I3. So I1 will be 6, I2 will be 3, and I3 will be 2 ampere. Now he's asking about the power delivered to each resistor and the total power delivered to the combination of the resistors. Okay, so what is the power delivered to the resistor? R1, which is equal 3 ampere. As you know, yeah. As you know, the power across the resistor can be equal to I squared R, which is equal delta V squared over R. Okay, which equation that we're going to use? Here we have the current and we have the potential difference. Which one we are going to use? We will use delta V over R. Why? Because delta V is already given and R is already given. So sometimes the students make mistakes in the calculation of I1. So why they use, for example, if they are making a mistake in the calculation, why they in this case they will use the wrong answer in the second question. For that, I prefer to use the given of the question, and we're gonna write P1 equal P1 is equal to delta V squared over R1, and will be 18 squared divided by 3. 18 squared divided by 3. The same for P2 will be delta V, because all of them, they have the same potential difference as they are connected in parallel. So it will be 18 squared divided by 6. And P3 will be 18 squared divided by how much? Divided by 9. 9 ohm. And we're going to get the power 108 for the first one, 54 for the second resistor, and 36 for the third resistor. And we have done. What is the total power delivered to the combination? Here we have only power supply, a potential difference, and we have resistors. So the total power delivered to these resistors is only the sum of the total of the power dissipated in each resistor. And we can add P1 plus P2 plus P3 to get the total power, because we don't have any other element in the circuit. So we're going to get 108 plus 54 plus 36 to get 198. We are done with this example. Let's move. Part C of this question said, calculate the equivalent resistance of the circuit. As we said, as we stated in the question, all these resistors are connected in parallel. So what will be the equivalent resistance? R equivalent in this case will be 1 over R1 plus 1 over R3. So let's write 1 over 3 plus 1 over 6 plus 1 over 9 power -1. So we're going to get 1.636 ohm. So R equivalent, as you see, it's smaller than the smallest. What is the smallest resistor in the circuit? It's 3. So R equivalent must be lower than 3. In our case, it's 1.636 ohm. It's okay, so we are done. Now, use R equivalent to calculate the power delivered by the battery, the total power delivered by the battery. The total power delivered by the battery is, as we said, delta V squared over R. Okay, delta V squared over R, because we have resistors. Okay, so delta V squared over R equivalent in this case, because he said this. So if we can substitute all of these 3 resistors by just one equivalent resistance, and this equivalent resistance is 1.636, and the power in this case would be delta V squared over R equivalent. So we can write 18 squared over 1.636 to get 198 watts. Here we can say, and we can notice that the total power delivered to the circuit is equal to the total power consumed by the 3 resistors. Okay, so we have the same thing. Let's move. In this question, he said 5 resistors are connected as shown. Find the equivalent resistance between the 2 points A and B. Okay, so he's asking to calculate the power, the total equivalent resistance. As you see, we have 1 ohm resistor and 1 ohm resistor are connected in. So they are connected. You see here that we have another resistor 5 ohm. 5 ohm in this case will be in the short circuit. Okay, the 2 sides, point C and point D, is almost the same. What about the 2 other resistors, 1 and 1? They are also connected in parallel, so the circuit will be like that. 2 parallel resistors and 2 parallel resistors. And here, it's like it's in the short circuit. Okay, in the short circuit. So we're gonna get R equivalent equal R equivalent 1 and R equivalent 2, both of them will be equal to 1 over 1 plus 1 over 1 power 1 over 1 over 1 power minus 1, so it will be equal 1 over 2. So we're going to get 1 over 2 series with 1 over 2 resistors. Okay, so the resulting resistance would be equal to 1 ohm. Okay, so we can say that the current in the AC and the AD is the same. Then the electric potential at the point C equals to the point D. For that, we said the resistor 5 ohm is in a short circuit. Potential difference between C and D becomes 0. So we can consider the point C is connected to the point D. The circuit becomes simple, and the equivalent resistance can be estimated to be 1 ohm. We are done. Now we're going to move to a more important part, Kirchhoff's rule. Kirchhoff's rule is the following. The first rule is the junction rule. The second rule is the loop rule. Let's define what means a junction. A junction is a point where 3 or more conductors meet. Okay? For example, if we have this conductor and we have a junction, how many conductors we have? We have 3 conductors. Let's say this is I1, this is I2, and this is I3. So according to junction rule, we can say that I1 is equal I2 plus I3 because at the junction, there is a conservation of charge. That means the current I1 entering the junction will be equal to the current I2 leaving to the total current leaving the junction, which is I2 plus I3. Now, what means a loop? A loop is any closed conducting path. If we have a closed conducting path, it's called a loop. Okay, we discuss one by one. The first rule is the junction rule. The sum of the current entering any junction in the circuit must be equal to the sum of the current leaving the junction. Okay, so here we have this junction. The current entering this junction, I1 for example, is equal to the current leaving I2 plus I3, so the sum of the current leaving. Okay, so the junction rule is a result of conservation of charge, because as you know, the current I is dq over dt. If we have a conservation of the current, that means we have a conservation of charge, and inversely. Charge don't accumulate at the junction, so the charges will be distributed over these two conductors. Okay. Now let's move to the second rule, loop rule. In the loop rule, we say that the sum of the potential differences across all the elements around any closed circuit loop must be equal to 0. So we can write that the sum of delta V across any element in the circuit equal to 0. How to calculate this delta V? Choose a direction of travel for the loop. Start from one point, go over all the elements in the loop till you return back to the starting point, and for each element express delta V equal V final minus V initial. So as a result, we can say that the sum of the potential differences across any closed loop is equal to 0. This is the result of loop rule is the result of conservation of energy. The charge don't gain or lose potential energies after traveling along a loop. So we can say that, as we said, delta V equal 0. If we multiply here by Q, if we multiply by Qi, what we're going to get? This quantity is the delta U, and we're going to get equal 0 because Q is different to the 0. So the loop rule is the result of conservation of energy. Junction rule is the result of the conservation of charge. Okay. Now, how to solve problems based on Kirchhoff's rule? At first, we have to draw the circuit diagram And this is the most important point in solving these kind of questions. And label all the unknown and all the known and the unknown quantities. You must assign a direction to the current in each branch in the circuit. And this direction will be assigned randomly, whatever it's clockwise or counterclockwise, okay? Apply the junction rule at any junction in the circuit and then provide an equation. Apply loop rule to any loops in the circuit as are needed to solve this unknown. For example, if we have three unknown, we need three equations. One equation will be coming from the junction rule if we have a junction, and the two other equations would be the result of the application of loop rule. Number of equations must be equal to the number of unknown to be able to solve this system of equations. Solve the equations simultaneously for the unknown, and I will give some examples. If the sign of the current in the branch is negative, the real direction of the current in the branch is opposite to that what you assign it, and we have to reverse the direction of the current. If the sign of electromotive force is negative, the real position of this electromotive force is opposite to what is supposed, and we have to reverse the electromotive force position. It's okay. So what are the most important point here? The first point is to draw the circuit diagram. The second point is the circuit diagram means that the potential differences across all the element of all the elements, and I will show you how. Okay, then we apply the junction rule, then we apply the loop rule until we get the number of equations equal to the number of unknowns. In this case, we can solve our problem. After that, if the resultant current is negative, so that means the real direction of the current is opposite to what we assign it. And if the electromotive force is negative, in this case, we can say that the real position of the electromotive force is opposite to what we assign it to. Okay, we're gonna take two examples or three examples in this lecture to try to apply the loop and the junction. Let's start by the first example. In this example, we said a single loop circuit consists of two resistors and two batteries as shown in the figure. Find the current in the circuit. So as you see here, it's a single loop. There is no junction rule, but we have loop rule. In loop rule, at first, we have to draw the free body, the circuit diagram. To draw the circuit diagram, please, we have to follow these two important points. The potential difference across the potential difference across the battery is from negative to positive. Okay, it's from the negative to positive. For example, here in the epsilon1, the battery epsilon1, the potential difference will be to this direction, and it's equal to 6 volt. For epsilon2, the potential difference will be to this direction, and it's equal to 12 volt. This is a very important point. The second point, the potential difference across the resistor is opposite to the direction of the current. Of the current, of course, going through this resistor. Okay, if for example we take a resistor and the current is in this direction to the right, for example, so the potential difference across this resistor will be to the left. We want to apply these two rules, and we want to see what we're gonna get. Okay, so as we said, the potential difference across the battery is from the negative side of the battery to the positive side of the battery. like that. Okay, what about the potential difference across the resistors? The current is going clockwise. So the potential difference across R1 will be opposite to the direction of the current. So it will be upward because the current in this branch is going downwards. And we can say that the potential difference across R1 will be the current I multiplied by the resistor 8I. Because as you know, according to Ohm's law, delta V across the resistor will be equal to the resistance multiplied by the current. Okay, let's continue. The current is going to the left in this branch DC, and it's going upwards in this branch AD. So the potential difference across R2 will be downward and equal resistance multiplied by the current I, 10I. Okay, we are done with the circuit diagram. Now we assign a positive direction. So let's take the clockwise direction as positive direction. Okay, and then we will see if we have a potential difference going with this positive direction will be considered positive, and if it's going to the opposite to this assigned direction will be considered as negative. So we can write epsilon1 is with the positive direction, so we can write 6 volt. Then let's go. The positive direction is going downward, but the potential difference is going upward. So we write minus 8I, because this is the potential difference across R1. We can write this is delta V1, and this is delta V2. Okay, let's continue. Now we have a battery, but the direction of the battery, the direction of the electromotive force of the battery is opposite to the positive direction of T-net. So we can write minus epsilon2, and epsilon2 is 12. Then let's continue. The positive direction is still clockwise, and the delta V2 is downward. So we can write minus delta V2, and delta V2 equal 10I. Are we done? No. We must write equal to 0, because according to loop rule, the sum of the potential differences across any element in the circuit will be equal to the 0. Here we have one equation with one unknown, so we can write, we can put the unknown in one side and the known or the given in the other side. So we have minus 8I minus 10I, so it would be 18I equal to minus 12 plus 6 minus 6. So we can say that the current I equal minus 6 over 18, which is equal 0.033 with the negative sign. So we can write minus 0.33 ampere. So here we see that the current is negative. So what we can conclude, we can say that the direction of the current, the real direction of the current is opposite to the assigned. It's okay. It's opposite to the assigned. So what will be the real direction of the current? The real direction of the current will be counterclockwise. Okay. In this case, we can determine which potential difference is producing energy and which one is consuming energy. Epsilon1 will be consuming or producing. Of course, will be consuming, because the current is entering the positive side of the battery. And we judge based on the real direction of the current. So this is consuming energy. What about epsilon2? Epsilon2 the current is going to the negative side of the battery. So here we can say that is producing energy. Okay, is producing energy because the current is going to the positive side of the battery. In this case, the potential difference is producing. Let's continue. Question B said, what is the power delivered to each resistor? And what power is delivered to the battery? To answer this question, we need the current. but we already calculated this current. Okay, so the current, as we said, I how much? The real current is 0.33 ampere. So we can say 33. Okay, so we can say that the power delivered to each resistor for the resistor R1, P1 equal I squared R1. So it's equal 0.333 multiplied by the current. This is the current squared multiplied by the resistance 8. For R2, P2 equal I squared R2. So it's going to be 0.333 squared multiplied by 10. And we're going to get, for the first one, 0.89, and for the second one, 1.11. 0.89 watts, and for the second will be 1.11 watts. We are done. Let's continue. What is the total power? What is the power delivered by 12-volt battery? Power delivered by 12-volt battery as you know, the power delivered by the battery is the electromotive force multiplied by the current. So it's going to be 12 multiplied by 0.333. And the result will be how much by 12 volt? Yeah, it will be 4 watts. It's going to be 4 watts. For the second question said, what's the power delivered by the second battery? The power delivered by 6-volt battery will be P equal epsilon. Let's write here epsilon 2, and this is epsilon 1. And let's write here 1. Okay, so it's going to be 6 multiplied by 0.333, and the result will be around 2. Is it 2? Yeah, it's 2 watts. 2 watts. Okay, now if we want to compute the total power delivered to the resistors, the total power delivered to the resistors will be equal P1 plus P2 because it's consumed. So we're going to get 2 watts. However, we said that the 6-volt battery is consuming. And the 4-watt battery is, the 12-volt battery is producing. So if we want to calculate the total power delivered, total power delivered to the circuit. So we're gonna, it will be what? Yeah, the 4 watt. 4 watt. Why? Because 2 watt will go to the resistors, and 2 watt is going to 6-volt battery because it's also consuming. And here we can say that we have a conservation of energy. Half of this power is delivered to the resistors, and half of the power is delivered to the 6-volt battery. We can say that epsilon 2 produces electric energy, while epsilon 1 consumes electrical energy, and this is the reason why. Because the current in the 6-volt, the real direction of the current for the 6-volt battery is going to the negative side of the battery, while for epsilon 2 is going to the negative side of the battery. In this case, we can say that epsilon 1 is consuming and epsilon 2 is producing. We are done. Now we will move to a little bit more complicated question. And here we have a junction and we have loops. Of course, the question will be always find the currents I1, I2, and I3 in the circuit. As usual, I want to discuss this question step by step. Okay. What are the steps? The first step is draw the Circuit diagram, as we said, for the battery is always from negative side to the positive side. For the battery, from negative side to the positive side. For the current, for the resistor, it's opposite. The potential difference across the resistor is opposite to the direction of the current. Let's start by this I1. I1 is going to the left or to the right, so the potential difference across 6 ohm resistor is to the right. And we can say this is the potential difference is 6 multiplied by the current going through this resistor is equal 6I. What about here? The current is going from the right to the left, so the potential difference will be opposite to this current I3. And it's equal to the resistor multiplied by the current going through it, 2I3. We have again here, the current is going clockwise. So this is the current I2. Okay, so the current is upward, so the potential difference will be downward, and it's equal to the 4 ohm resistance multiplied by the current going through this resistor, 4I2. Okay, so we are done with the first step. Draw the circuit diagram. Now let's move to the direction. We will assign a positive direction clockwise, for example, for the 2 loops. Here, actually, we have 3 loops. Okay, and then we will apply junction rule. Junction rule, the 3 currents at which point? At the point C, because the 3 currents, they meet at the point C. Okay, the sum of the currents entering the junction is equal to the sum of the current leaving the junction. How many current is entering and how many is leaving? We have for the entering is I1 and I2, so we can write I1 plus I2 is equal to the current leaving. How many current is leaving? We have only I3. Put it in the box and label it as equation number 1. So we are done with the junction rule. Now let's move to the loop rule. But as I said, we have 3 loops. We have 3 unknown, I1, I2, and I3. So we need 3 equations. We will apply the loop rule on the upper loop and the lower loop. And like that, we're going to get 2 equations with the first equation and means 3 equations, 3 unknown, and the system can be solved. Okay, loop rule. On which loop? The upper loop. Good. So here we assign the positive direction to be clockwise. Okay, so we can say that 14 volt is opposite to the positive direction, so we can write minus 14. Then we don't have any element here between C and F. Then let's move between in the branch BC. We have a resistor, and the potential difference across the resistor is 6I1 because it's with the positive direction, so we can write 6I1. Then minus 10 because the electromotive force is to the right, and the positive direction, as we said, for this closed loop is to the left in the branch of BC. So minus 10 volt, and then minus 4I2, and of course equal to the 0 because the sum of the forces, the sum of the potential differences across the closed loop must be equal to 0 to conserve the energy. Good. So here we can arrange this equation to write the unknown in one side and the constant in one side, and we can simplify also by 2. Okay, we can simplify by 2 to get the following. Minus 14 over 2. So, okay, so minus 14 minus 10, it would be 24 over 2. So it will be 12. So we're going to write 12 equal, or let's write on the left side of the equation the unknown. 6I1 divided by 2, it's 3I1 minus 4I2 divided by 2 minus 2I2 equal 12. Good. This is our second equation. Let's apply the loop rule on the lowest loop, on the lower loop. Loop rule. in the lower loop. What we're gonna get? Of course, here with 10 volt, in this case, it will be clockwise with the positive direction, minus 6 I1, minus because it's opposite to the positive direction, assigned in the lower loop. Here we don't have anything, minus 2 I3 equal 0. We are done. So here also we can simplify by 1 over by 2, and we can put the unknown on one side, on the left side, to get 3 I1 minus I3 minus I3, sorry, plus I3 to be equal 10. So this is our third equation. So now we have 3 equations and 3 unknown. So we can write the equations like that. We forgot to simplify here 10 by 2. So it's 5. Yeah. So the 3 equations will be the following. Now just we want to play with these equations to solve the unknowns. Okay, how to solve the unknowns here? So you see that we have 3 equations. We have I3, and here we have I3. I3 is equal I1 plus I2. So we will substitute I3 in the equation 2. So we can write I3 in equation 2 to get 3I1 plus I3, and I3 is I1 plus I2. I1 plus I2. This will be equal 5. And we're going to get a fourth equation. So 3I1 plus I1, so it's 4I1 plus I2 equal 5. This equation would be equation number 4. So now we have a new equation, and we have a third equation that we did not use it. So we're going to use these 2 equations to simplify one unknown and to get an equation with a single unknown. So you see here that we have, for example, minus 2I2, and here we have I2. So we can multiply by 2 and we add. So equation 3 plus 2, equation 4. 2 times equation 4. What we're going to get? We will get 3I1 minus 2I2 multiplied by 2. So that means plus 8I1 plus 2I2 equal 12 plus 10 plus 5 times 2. So here we can simplify by, which one will we simplify? Okay, 2I2, 2I2. So we're going to get 3 plus 8, it's going to be 11 I1 equal 12 plus 10, 22. So that means I2 equal, I1 equal 22 over 11, which is equal 2 ampere. So we are done. I1 is equal to 2 ampere. So I1 equal to ampere. Now we will use this I1 in one of these equations to get whatever I2 or I3. I prefer to get I2 because we will add I1 and I2. So here I1 equal 2 ampere in equation, for example, 3. We're gonna get 3I1, that means 3 times 2 minus 2I2 equal 12. So that means 6, and here we have 12, so it will be minus 6, and we can write 2I2 equal minus 6. So that means I2 equal minus 6 over 2, which is equal minus 3 ampere. And this is our second current, yeah, minus 3 ampere. Now, just we add the 2 currents. So for I3, equal I1 plus I2. We're gonna write I1, we said it's 2, I2 is minus 3, so it's equal minus 1. Okay. So here we see that I1 is positive, so this is a real direction. And I2 is negative, so opposite to the real. The assigned is opposite to the real. The same thing for I3, which is also opposite to the real direction. The assigned direction is opposite to the real direction. Okay, the fact that I2 and I3 are both negative, this indicates that these currents are opposite to the direction we choose for them. Or we can say opposite to the assigned directions. We are done with this example. Now we will treat another example. Under steady state conditions, find the unknown currents I1, I2, and I3. Very good. As usual, let's try to do the example step by step. The first step, as you know, is the drawing of the circuit diagram. As we said, across the potential difference, across the battery, the potential difference is going from negative to the positive. Okay, from negative to the positive. Across the battery, across the resistor is going opposite to the current. So here is the down equal 5, and the current is I3, 5 I3. Here it's going to the left, so the potential difference is going to the right, equal 3, and the current is I2. The potential difference is going downward, so the current is going downward, so the potential difference will be 5 I1 and directed upward. That's all. Here we have 3 unknowns, so we need 3 equations. Similarly, here we have a junction at a point, junction rule. At which point? At point C. Okay, so what do we have as junction rule? The sum of the current leaving is equal to the sum of the current entering. So we can write I1 is entering plus I2 is entering will be equal I3 leaving. And this is equation number 1. So as you know, we have 3 unknowns, so we need 3 equations. What about the loop rule? Loop rule here, we see that we have many loops. This is 1, 2, 3, 4, 5. Okay, so we have many loops. Which loop we will use? We will use the upper loop and the middle loop. Why? Because the current in the lower loop is equal to the 0. Okay, so we're going to use these 2 loops as before. So here, let's start by the upper loop. What we're going to get in the upper loop, at first, let's assign a positive direction. Any potential difference going with the positive direction will be positive. Any potential difference opposite to this assigned direction will be negative. So the 4 is going with the positive direction, so we write +4. Here we don't have any element in the branch FC, FE, and here we have a resistor, and the potential difference is going to the right, and the positive direction is clockwise, so it will be -3I2. Let's continue. We don't have anything. Here we have, -5I3 equal 0, because we are coming back to the 4-volt battery. So we put the unknown in one side and the given in one side. We're going to get 3. We cannot simplify here because we don't have any common multiple. 3I2 plus 5I3 equal 4. This is equation number 2. For the lower loop, for the middle loop, what we're going to get? Positive direction also clockwise. So 3I2 is going with the positive direction, so we can write 3I2, then -5I1. Let's continue, +8 volt, and we don't have anything, and we close the loop to be 0. So here also we cannot simplify, and we can say that 5I1 -3I2 equals 8 volt. So this is our third equation. So we see here that we have 3 equations and 3 unknown. So we can simplify. Let's write the equations here. Good. What are the equations? Yeah, equation number 1, 2, and 3. Do it by yourself. Very good. Okay, so as before, we will use this I3 in one of these two equations. So I3 in the equation number 2. So we can write I3 in equation 2 to get 3I2 plus 5I3. And I3 is I1 plus I2 equals 4. Yeah. So 3I2 and 5I1 plus 3I2 and 5I2, so plus 8I2 equals 4. This is equation number 4. So now we have two equations not used, equation 4 and equation 3. So we're going to do some arrangement between equation 3 and equation 4 to get an equation with a one unknown. So you see here that we have 5I1 and 5I1. So if we subtract the two equations, equation 3 minus equation 4, we will get 5I1 minus 3I2 minus 5I1 plus 8I2. This is equation 4 to be equal 8 minus 4. What we're going to get? Here we can simplify by 5I1 and 5I1. So we're going to get minus 3I2 minus 8I2 minus 3I2 minus 8I2. It would be minus 11I2. So we can write minus 11I2 to be equal 4. So that means I2 equal minus 4 over 11. It's going to be how much? I2 minus 0.364. So I2 will be minus 0.364 ampere. We are done. This is for I2. You see that I2 is negative, so the real direction will be opposite to the assigned direction. So I2 in one of these two equations, in equation, for example, in equation 3, to calculate I1 gives 5I1 minus 3 multiplied by minus 0.364 to be equal 8. So we can write I1 will be equal 1.38 ampere. Good. Just calculate this equation using your calculator. What about I3? For I3, and don't forget from equation 1, I3 equal I1 plus I2. So we're going to write I1 1.38 minus 0.364. How much it would be? It would be 1.02. So it will be 1.02 ampere. And it's positive. So we can say that the real direction is for I1 and I3 is the same as assigned, but for I2 is opposite to the assigned direction. We are done. Let's move to the second part of this problem. What is the charge on the capacitor? The capacitor is connected in the lower loop. So now we will work on the lower loop. Okay. So as you know, here we have no current. Why we don't have any current? Because if the capacitor is fully charged, in this case, it will work as an open circuit. Okay, and the current will be equal 0. Let's draw the circuit diagram The potential difference across the 8-volt battery is from negative to positive, the same for the 3-volt battery, and the same for the capacitor. Let's apply the junction rule, the loop rule, sorry. But before, why we are applying loop rule? As you know, C equal Q over delta V. That means Q will be equal C delta V. C we know it's 6 microfarad, but we don't know delta V. Delta V from where? From we get delta V from the loop rule. Loop rule, which loop? The lower loop. Okay, we're gonna get -8 because opposite to the assigned direction, plus delta V of the capacitor, the potential difference across the capacitor, which is equal, minus 3 equal 0. So delta V across the capacitor will be equal 11. And this 11 volt in the other side is equal to this 11 volt. Okay, so we are done. What we want to calculate, we want to calculate the charge. Q equal C delta V C. So that means it's equal C, 6 microfarad, multiplied delta V is 11. So Q in this case would be 66 times 10 power negative 6 coulomb. It's okay, or we can write 66 microcoulomb. We are done. Okay, so I think there is another question. Reverse the direction of the 3-volt battery and answer the part A, B, A and B. Okay, so here we said reverse the direction of the current. Okay, the direction of the 3-volt battery. If we reverse the direction of the 3-volt battery, it would be like this. Okay. And the potential difference across this 3 volt, it will be to the left. And the potential difference here to the left, also here to the left. So there is no effect on the current I1 and I2 and I3 because here the current in this loop is 0. And the battery is connected to the lower loop. So there is no results or it will not affect the current I1, I2, and I3. Let's apply the loop rule. So we're gonna write -8 and then plus delta V across the resistor, the capacitor, plus 3 volt in this case, not minus 3 volt, equal 0. So delta V across the capacitor will be equal 8 minus 3, which is equal 5 volts. Okay. However, we know that the charge is C delta V across the capacitor. It's going to be 6 times 10 power negative 6 microfarad, multiplied by 5, which is equal 30 microcoulomb. Okay. We are done. Let's move. We have another circuit, call it a bridge circuit. The circuit below shows a bridge circuit. Find the current in each resistor, then find the equivalent resistance of the network of the 5 resistors, and what is the potential difference VAB. Okay, let's try to do or to answer these questions step by step. At first, we will apply the junction rule and the loop rule, but here it's a little bit more complicated. But in the reality, it's not too much complicated. Okay, so we have 3 loops, and we have current I1, I2, and I3. So we can get 3 equations, and we can solve. If, for example, we apply the junction rule here, what we're gonna get? We're gonna get I1 minus I3 plus I2 plus I3. So here I3 will be cancelled. So we're gonna get I1 plus I2. And here it's I1 plus I2. So there is no benefits of applying junction rule. So what we're gonna get? We're gonna write loop rule. On which loop? Loop 1. We have 3 loops. Okay, loop 1. But before, let me draw the circuit diagram. for the circuit diagram, okay. For the circuit diagram, the potential difference will be from negative to the positive as usual. Then let's go. We have one ohm resistor and the current is going down. So the potential difference will be up. And the potential difference will be 1 multiplied by I1, the current multiplied by the resistance. Let's continue. Here we have I1 minus I3 and the resistance is 1. So the potential difference will be opposite to the current. And we're going to write 1 multiplied by I1 minus I3. Here we don't have anything. Let's continue. The potential difference across this, it will be opposite to the current, and it will be 2 multiplied by I2 plus I3. Okay, the potential difference across this one resistor, 1 ohm resistor, will be opposite, and it will be equal I1 1 multiplied by I3, current multiplied by the resistance. Here it's also opposite to the current, and it will be 1 I2. Okay, for the first loop, this is the positive direction, it's clockwise. We have 13 with the positive direction, then minus 1 I1, so we're going to write I1, but here we don't forget that we are multiplying by the resistance 1. It's not current, it's a potential difference. So let's write 1 I1 to avoid any confusion, because it's not possible that we add a potential difference with a current. So we will add potential difference and potential difference. But in our case, the resistance is 1. So we can assume like that. We can write like that. It's better than writing 1 I1. Okay, then it's going through the 1 ohm resistor. So it will be plus, no, it's minus I1 minus I3 equals 0. So we will write here 2 I1 minus I3 equal 12. This is equation number 1 from loop number 1. Loop 2, what is loop 2? Is the total loop. So here we have, it's also clockwise, 13, equal 13, not right. 13 minus I2 minus 2 multiplied by I2 plus I3 equals 0. So how many I2 we have? We have 3. So let's write 3 I2 plus 2 I3 equal 13. This is equation number 2. Loop 3. What is loop 3? Yeah, it's here. So it's counterclockwise the positive direction now. So we can write I2 minus I1. Yeah, minus I3 equals 0. So we can write I2 equal I1 plus I3. So now we have 3 equations and 3 unknown. Okay, what are these equations? Okay, let me write here. So if we use, for example, equation 3 I2 in, if we use I2 in equation 2, I2 in equation 2, we're gonna get, what is equation 2? Equation 2 said 3I2, and I2 equal I1 plus I3 plus 2I3 equal 13. So in this case, we're gonna get 3 I1 plus 5i3 equal 13. And this is equation number 4. Now we have equation number 4 and equation number 1. So we have to arrange these two equations. 5i3 and yeah, if we multiply this equation by 5, so we can write equation 4 plus 5 equation 1. Why? Because we want to cancel this i3. We're going to get 3i1 plus 5i3. And then, what do we have? Why it's written here? Okay, whatever. 2i1. So that means 10i1 minus 5, 10i1 minus 10i1 plus 10i1 minus 5i3. We're going to get 13 plus 5 multiplied by 13. Is it okay? 5 multiplied by 13, yeah. By 13. That's all we are done. So now we can simplify this 5i3, 5i3, and we're going to get 13i1 equal this will be 5 multiplied by 13. It will be 65 plus 13. It's going to be 79, 78. Good. So that means I1 equal 78 divided by 13. How much? I1 will be 6 volt, 6 amperes. Sorry. We are done. Now we can put I1 here in equation 4, for example. I1 in equation 4, and we're gonna get 3 multiplied by 6 plus 5 I3 equal 13. We're gonna get I3 equal 13 minus 18. 13 minus 18 minus 6 divided 13 minus 18, so minus 5 divided by 5. So it's minus 1 ampere. Yeah, is it correct? Yeah, I3 equal, yeah, minus 1. And what about I2, which is equal I1 plus I3? It's gonna be I1, we said it's 6 minus 1, it's 5 ampere. And like that, we are done. Okay, so we are done with this kind of examples. Now we're gonna move to some class activities. Okay, now we will talk about the class activities and we will try to answer these two questions. Question 1 said, which of the following two arrangements shown has the smaller equivalent resistance between the point A and B? Okay, as we said before, for the series combination, R equivalent is higher than the smallest resistance. And R equivalent for the parallel combination is smallest than any individual, sorry, here it's higher than the highest, not the smallest, highest, higher than the highest individual resistance in the circuit. And this is smaller than the smallest. Good. Okay. He's asking to give smaller equivalent resistance. So of course it will be parallel combination gives the smaller equivalent resistance. Let's move to the second. 3 identical resistors. Each resistance has R, are connected as shown. What is the equivalent resistance in this configuration or in this arrangement? So if we write here R, these two are parallel, and for the parallel it will be R equivalent for the parallel combination, it will be R divided by the number, which is 2. Now we're going to get a parallel with the series plus R. Okay? And this will be the total equivalent resistance. Good. So it's going to be 3R over 2. We are done. Thank you so much. See you the next time.